trig substitution. Up to this point, we've always had x squared by itself. And the question is, what do you do if you have something other than, can you still use this technique if you have something than just x squared? And the answer is yes. So you still have here, you have a term that involves the variable x squared with this constant, and then you've got the constant term. So because we're adding stuff together, we're going to use the tangent, and the substitution we would make is the tangent of theta is equal to 2x over 3, because if I square 2x, I'll get 4x squared. And remember, all this stuff relates to the Pythagorean theorem, so if we let the opposite side be 2x and the adjacent side be 3, then 3 squared plus this squared, which is 4x squared, equals the hypotenuse as far as lengths are concerned. So that's the only difference. So it's just, so we'll get 2x equals 3 tangent theta, or x equals 3/2 tangent theta. So we just end up with some, instead of whole number constants in front of tangent, we're going to end up with a fraction. But the rest of it's the same. So you take dx would be 3/2 secant squared theta d theta. The trig function involves the ratio of the square root term to the constant term is going to be hypotenuse over adjacent, which is the secant. So that means that the square root of 4x squared plus 9 is equal to 3 secant theta. So then we got now we have all the substitutions we need. So we'll plug that in there. So for that, we'll plug in 3 secant theta. For dx, we'll stick in 3/2 secant squared theta d theta. And for x, we'll put in 3/2 tangent theta and raise that to the 4th power. So it's not a whole lot of simplification we could do. Let's pull all the constants out front. So you can have 3 times 3/2 times, what I'm going to do is I'm going to take the reciprocal of this, 2/3, raise it to the 4th power. So that handles all the constants. And then we end up with secant cubed over tangent to the 4th power. Okay, so now we got to figure out how to solve that trig integral. Like I said, the main purpose for learning section 3 was to be able to do trig integration for trig substitution more so than actual. You won't see these kinds of equations pop up that much if you're solving some problem. Things like this are more likely algebraic things are more likely to turn up, but to be able to solve them, you have to put it in terms of trig functions. So let me think, what could I do? I'd probably just change it to sine and cosine and see what happens. So what we'll have is 1 over cosine theta. I'm going to change the exponent so that it shows you're cubing the actual function. So this is the shorthand version. That's the longhand version. Okay, then we have sine of theta. So tangent is sine over cosine. So you get sine of theta over cosine theta, both raised to the 4th power. And so that's the same as multiplying by the reciprocal. So we get cosine theta to the 4th power. I'm going to mark that out just a second. I should have probably just rewritten it, but I got lazy there. Okay, so I've replaced that division by the multiplying by the reciprocal. So what we're left with now is 1 over sine of theta to the fourth cosine theta d theta. What I'm doing, I just went and did the stuff inside the integral. And then what do we have here? We have, if we simplify that, you'll get 2 cubed, because this 2 to the fourth cancels out with one of the 2's in the denominator, the 2 in the denominator. And then here you have 3 squared divided by 3 to the fourth, so that's going to be 3 squared in the denominator. Okay. So now the question is, can I solve this? And the answer is yes. You let u equal the sine of theta and du equal the cosine of theta d theta. So we have to use u substitution. I mean, most of the, in this case, it's something we would have been able to do back in chapter 4. We didn't, because we don't have to use any trig identities, or we've just got a function and the derivative of the function. So it's just a straightforward u substitution problem at that point. So so now we'll rewrite the integral in terms of u. So that's 8/9. So go ahead and multiply the thing out in front here. So we'll have 1 over u to the fourth du, which is the same. We'll have to change that to a negative exponent, u to the minus 4 power du. So we add 1 to the exponent. So we get u to the minus 3 power divided by the new exponent, which is negative 3. Add our arbitrary constant c at that point. So we'll get negative, take the negative, move it out front. 8 over 27, 9 times 3 is 27. And I'm going to go do 2 steps here. So u to the minus 3 power is 1 over u cubed, but u was sine of theta. So it's 1 over the sine of theta cubed. So that gets it back in terms of theta. And then I have to go back and look back at my original substitutions to find out what the sine of theta is in terms of x. Well, we don't have that in our original 2 substitutions here, so we have to look at the triangle and say the sine of theta, which is the opposite over the hypotenuse, in terms of the lengths defined here, are going to be opposite over hypotenuse. So that's what the sine of theta is. 2x divided by the square root of 4x squared plus 9. Okay. So the sine of theta equals 2x divided by the square root of 4x squared plus 9. So when I plug that in finally, I'll get negative 8/27 times 1 divided by 2x over the square root of 4x squared plus 9 cubed. And I can clean this up a little bit, because 2 cubed here is 8, which cancels out with that. So I think and this cube, I can take the reciprocal of this and put it up in the numerator. So what I end up with, I think, is 4x squared plus 9 to the 3/2 power divided by x cubed, and then times 1/27, I think. Yep. Okay, so try to follow me on this again. This 2 cubed is 8. That cancels out with that 8. This x cubed is in the numerator in this fraction, so it stays in the denominator. I take this and I move it to the numerator by taking the reciprocal of this whole thing. Here I have 4x squared plus 9 to the 1/2 power cubed. So that's the same as 4x squared plus 9 to the 3/2 power. Did I get that right? Anybody follow me? Evan, did I get it right? Okay. So does that, let's look back at the original integral. Does that kind of make sense to some extent? Yeah, it's actually cleaner than you might think it would be. So yeah, let's go through the whole thing again just to make sure we understand what's going on. So when we do have an argument for the variable term that's not just x squared, it's not a problem. We just take the square root of that term. So the square root of 4x squared is 2x, and the square root of 9 is 3. So and again, because they're added together, we use the tangent. So we say the tangent of theta is equal to 2x over 3. We always put the variable, some people make the mistake and they put 3 over 2x, but we always want the variable part in the numerator. Okay, I don't know how that happened. I guess I need to.
To make us perk us up a little bit this year. Summery kind of songs. And I know they did typically tropical going to Barbados, but Richard in Derby also sent it Rainbow Val.
I'm hearing this little English accent coming out of my pocket. Okay, anyway. So with that, we make the opposite side 2x, the adjacent side 3, such that when we use the Pythagorean theorem, the hypotenuse is the square root of 4x squared plus 9, which is what we're looking for as a substitution. So we solve for x. The only difference is from what we've been doing is you end up with a fraction instead of a whole number. Take the derivative like we normally did, find the trig function, it's the ratio of the square root term to the constant term, which is the hypotenuse over the adjacent, which is the secant. Solve for that. Turns out it's 3 secant theta. We stick it all in there. We simplify down to this, and then we try to figure out what the heck we're going to do. We've seen that quite often just putting it in terms of sine and cosine makes the most sense. But not always. And you're probably worrying, yeah, I see it when you do it, but I don't think I could do it myself, right? And usually on the tests, I don't put one that's that hard, okay? So if you can figure it out, great. But if you can't, if you looked at that and said, I have no idea what to do, don't worry too much. You won't suffer for it as long as you understand the basic procedure. And a lot of times in these, unless it's just a simple trig integration like the integral of the sine or the cosine, you have to sometimes use u substitution to do the actual integration. The trig integration involves u substitution, so you end up actually doing the integration not with the trig functions but with the polynomial that you get when you do the u substitution. So then we have to go back and do 2 substitutions. First to get the equation from in terms of u back in terms of theta, and then from theta back in terms of x. Okay. Another thing that could happen is this. This one's already factored, but if I let me multiply this out just to show you. If I take the denominator and the square root there, it would be 9 minus x plus 1 squared, which is 9 minus x squared plus 2x plus 1. If you multiply that out, so you'll get 9 minus 1, which is 8, minus 2x minus x squared. So the original argument in the square root could have been this. And so what you have to do is first get it into a form where you have a squared plus or minus u squared, or u squared plus or minus a squared. Now we can handle all of those cases. Back in chapter 5, we could only handle a limited number. So just like in the previous problem, where the argument, the part that was involving the variable, we took the square root of that to figure out what we needed to use to construct our triangle. In this case, the same thing's true. So instead of x being the length of one of the sides of the triangle, x plus 2 is going to be one of the sides of the triangle. And because it's 9 minus, we're going to use the sign to get such that the third side ends up being this value. So we're going to say that the sine of theta is equal to x plus 1 over 3. So the square root of x plus 1 squared is x plus 1. The square root of 9 is 3. So we get, and we're using the sign, so we have x plus 1 over 3 no, just x plus 1. I was like, what am I doing? Okay, so the numerator is the opposite. The hypotenuse is the denominator. I mean, the hypotenuse is the denominator. Denominator is the hypotenuse. And when you find the third side, you'd end up with 9 minus x plus 1 squared. So if we multiply, we'll get x plus 1 equals 3 sine theta. So we still have to solve for x. So we're going to have to subtract 1 from both sides. It doesn't add, well, let's see what happens. Actually, it could get kind of interesting. So you get x is equal to negative 1 plus 3 sine theta. So dx is going, this goes to 0. So you get 3 cosine theta d theta for dx. And the ratio of the square root term to the constant term, in this case, it's the adjacent over the hypotenuse, which is the cosine of theta. So the square root of 9 minus x plus 1 squared is equal to 3 cosine theta. So the only one that is any more difficult than before is this one, because I've got this extra constant in there. When I take the derivative, the constant disappears. And for this one, the constant stuff is inside the square root, so I just end up with 3 cosine theta. So it's slightly more difficult. Okay. So now we make the substitution. So we'll have x is negative 1 plus 3 sine theta. We square that. And then we multiply by dx, which is 3 cosine theta d theta divided by the square root of 9 minus x plus 1 squared, which is 3 cosine theta. Okay, so now you can cancel out those, thank goodness. So it's not quite as bad as I thought it was going to be. So what you end up with is negative 1 plus 3 sine theta squared d theta. So what we're going to do is we're going to just use FOIL to multiply that out and then look at each individual integral. So we'll get, you'll get 1, negative 1 squared is 1. You'll have negative 3 sine theta, negative 3 sine theta again, so you'll have negative 6 sine theta, and 3 sine theta times 3 sine theta is 9 sine squared theta, and that whole thing is times d theta. So the first two are pretty easy. We're going to get theta. When you integrate one, you get theta. The second one you're going to integrate, you'll get cosine of theta. And the third one, we have to use one of those power reducing formulas, which, Christian, I have something for you, because I remembered. I think it, what's that? Yeah, I know. So if anybody needs another one of these things, so amazingly I remembered. I must have done it first thing when I went over. Yeah, so if you look on that sheet, you'll find out. Does that have copies both sides, or did I give you the original? Okay, because this one only has one side. So I have to find another one here. Okay, so we look at power reducing formulas. So this term here, so what we'll have is 1 minus 6 sine theta plus 9 times, and the power reducing formula is 1 minus cosine of 2 theta over 2. And that whole thing times d theta. So actually we can take 1 plus 9 halves. That'll give us a constant. So 1 plus 9 halves, that's 11 halves. So we'll have 11 halves minus 6 sine theta minus 9 halves cosine 2 theta, all times d theta. Okay, I think that's right. Okay, so now we'll integrate. So what you'll get 11 halves theta minus 6 times minus cosine theta. So the integral of the sine of theta, if you look on the other side of your sheet, is negative the cosine of theta. And here we'll get 9 halves. When we integrate this, we'll get the sine of 2 theta, but we'll have a factor of 2 that we have to take into account because of u substitution. So we divide by 1/2, so we'll get sine of 2 theta plus c. Okay, now remember when you have just theta by itself, you go back here and you look at what the original substitution was. So we're going to take the inverse sine or the arc sine of theta to find theta. So what we can say is theta is equal to the arc sine of x plus 1 over 3. So let's substitute that in. So this is going to be 11 halves the arc sine of x plus 1 over 3. Okay, the next one, these negatives cancel out, so you get plus 6 cosine of theta, but the cosine of theta is equal to square root of 9 minus this thing here. So we'll plug that in there. So that's going to be equal to the square root of 9 minus x plus 1 squared divided by 3. And then the final one is going to be 9/4 times the sine of 2 theta. So there's a problem. It's not a problem because I know the answer, but for you guys it would be a problem because you're like, I know what the sine of theta is. I know what the cosine of theta. I can find all of the numbers associated with the sine, the trig functions of theta by going back to my original triangle, but I've got the cosine of 2 theta. So anybody have any idea how I would handle that? Look on your sheet on the trigonometry page. Do you see anything that says sine of 2u? Yep, so it's a double angle formula. There's only one choice. So using the, so what I'm going to do is I'm going to do this over here separately just because I want to put the answer here. So what we have is that the sine of 2 theta is going to be equal to 2 sine theta cosine theta. So we'll have is 2 times the sine of theta. Go back here again. The sine of theta is x plus 1 over 3. So we're going to get 2 times x plus 1 over 3 times the cosine of theta, which I already have. That was equal to the square root of 9 minus x plus 1 squared over 3 plus c. Yeah. Obviously, I'm not going to give you this on the test either, but you know, it looks. That's why I think trig substitution is so cool, because I mean that is super complicated looking. I mean, it has trig functions, it has polynomials, square roots, and I could simplify that last term, but I've just left it as it is right now. But you know, that we could go through this whole thing and actually get a solution. And if I wanted to find the slope, you know, originally the whole idea, well, here I'm finding the integral, so I'm finding the area underneath the curve. So this curve, whatever it looks like, what does this curve look like? X squared divided by, let's see what it looks like. Because you get kind of hung up in the mechanics of doing this, but you forget what the purpose is. The purpose is you want to find the areas underneath the curve so that you can find the energy or the momentum change or whatever these things are that we learn in physics. So let me let's look at it. Let's see what it's. So x squared divided by the square root of 9 minus x plus 1 squared. There we go. I think that's right. X squared over square root of 9 minus x plus 1 squared. Okay, let's see what this thing. So that's what it looks like. It's kind of it looks like a parabola, but it's kind of skewed one direction. So what we're looking at is if I want to find the area underneath this curve, say this, I draw a vertical line here, maybe go from the origin from 0 to some value of x, which can't be very big because it actually has a vertical asymptote here at 2, I think. So we could only go from 0 to somewhere below 2. But that integral that we just came up with gives us the area underneath that curve. So again, it's fairly complicated, so I'm just going to talk through it again just to convince myself that I did it right. So I've got x plus 1. Okay, so again, we have determined the square root. Take the square root of the term that involves a variable, which is x plus 1. We divide by the square root of the constant term. We make this the opposite length, side length. This is the hypotenuse side length. The adjacent side length is going to be 3 squared minus x plus 1 squared square root, so that's right. Multiply both sides by 3. Subtract 1. Get that. The derivative of that is that. The ratio of the square root term to the constant term is adjacent over hypotenuse, which is cosine. Multiply by 3. Plug those in there. That looks right. Luckily, the cosines cancel out. We use FOIL to multiply this out. Use the half angle formula to get this in terms of something not raised to a power. The reason is because if we had cosine over here, that'd be great, but we don't have cosine, so we have to use the power reducing formula, which I use the correct one. And then I said 1 plus 9 halves was 11 halves. Negative 6 sine theta. 9 times negative 1 half, negative 9 halves, cosine 2 theta. That's right. Integral of 11 halves is 11 halves theta. Integral of cosine, sine is negative cosine. This you divide by a half because of this. It'll go cosine and sine. Theta is the arc sine, yeah, that's right. Negative 6 times negative, that's right. Cosine theta is that. 9 halves times a half is 9 fourths. Where did that come from? Oh, from here. So I always have to, I had to use the half angle to do the integration, but then you always have to go back and use the double angle or the power reducing to get so that you can do the integral, and then you have to use the double angle formula to convert it back to theta. And the sine was x over, yeah. Okay, that looks right. I'm trying to think if there's any. Well, let's see if you guys can do this one next, just as a finishing problem. So we're going to do this last one on the right hand side. And if you look back at your problems from the other day, well, I just ask you guys, what trig substitution do we use? Sine, tangent, or secant? So when we add them, they're tangent. We just did the sine. That's where we subtracted the variable part from the constant part. Here we're taking the variable constant part, subtracting from the variable part. So the only one we got left, process of elimination, this is the one we use maybe less often, is going to be the secant. So the secant of theta is just x over 4. Okay, so go ahead and try to work the rest of it. I'll give you 5 minutes head start. Secant is hypotenuse over adjacent. That's another reason I like trig substitution, because it requires you to use a lot of what you learned in pre-calculus. Trig substitutions. What else did we use? Just trigonometry in general. Pythagorean theorem. Since we're driving today, I didn't bring my coffee in. My coffee. Oh yeah, we also use a lot of derivatives. You know, you have to get dx, you have to take derivatives, which we So that's probably where you're stuck, right? What do I do? So this is a case where there's no point in trying to write it in terms of cosine because it's still going to be. But the key thing to notice is that this is even. So we can rewrite this secant. If we took secant squared, yeah, actually that will work out fine. So remember, the derivative of the tangent is the secant squared. So you can take secant squared, put that with d theta, and then you're going to use the appropriate trig identity to rewrite the other part of the secant squared. So you got two secant squareds here, which gives you secant to the fourth. So this is the derivative of the tangent. So if I can get this in terms of the tangent, or even if I the tangent and a constant, then I should be able to solve it. So you'll go to your trig identity page here, look under Pythagorean identities, and you see the secant is equal to 1 plus the tangent squared. So you get 64 times the integral of 1 plus tangent squared theta times secant squared theta d theta. And so that's really two integrals. The integral of secant squared theta d theta. So this 1 times secant squared gives you secant squared. And then the second one is tangent squared theta times secant squared theta d theta. So this one is in your table of integrals. And this one you can use U substitution. So I'll let you finish the rest of that. But again, it's just something I'm a lot better at it than I was 7 or 8 years ago. Not that I remember the problems exactly. It's just like a language. You get used to it. I always think what it would be like going back to college actually knowing calculus instead of, I got an A in calculus, but now I know that I didn't really know it that well. It'd be kind of interesting to see how I'd understand what I was doing better. So once you integrate it, then you can go back and find the, then you have to put it back in terms of x, so don't forget to do that. My daughter's worried about us driving today. I told her I don't see any accidents. Hopefully not many truckers are driving today. Must be getting snow in New York. There's all kinds of lousy traffic. Okay, here we go. Okay, I think that's right. So we use the Pythagorean identity to change secant squared to 1 plus tangent squared. Multiplied that out, got two integrals. The integral of the secant squared, which is the tangent, that's one of our known integrals. Here we had to use u substitution, so we have tangent theta being u, du is secant squared theta d theta, so that becomes u squared over u squared du, the integral part does. So that's now polynomial integration. So you integrate u squared, you get u squared over 3 plus c. And but u was tangent theta, so I get tangent cube theta over 3 for this part of the integral. And then I have to use the original trig substitutions. They're both tangent, which is nice, so I looked back at my original drawing, and the tangent was the opposite over the hypotenuse, which in this case was the square root of x squared minus 16 over 4. So I put that in for tangent theta, and then I cube it, and so I forgot that part. So when I cubed the top, the cube of a square root is to the 3/2 power, so I'm missing 4 cubed in the denominator. So this would be 64, which means those would cancel out. And so 64 divided by 4 is, what is it, 16? Yeah. So that becomes 16 times the square root of x squared minus 16 plus 1/3 x squared minus 16 to the 3/2 power plus c. Okay, so that's it for right now for trig substitution. We're going to go to the next section, which is partial fractions. We looked at this, a brief review of partial fractions back when we talked about logistic growth, because we had to use partial fractions to solve for the equation, which we never, we didn't require you to remember how to solve for it, but we did it. But the whole idea behind partial fractions is you have a rational number where the denominator is squared, and what you can do, the concept is you can rewrite a single fraction that can't be integrated as multiple fractions that can be integrated. So that requires that you're able to factor the denominator. Sometimes you can factor it, sometimes you can't. You can factor it if they're real zeros. If it's a quadratic that doesn't have real zeros, you can't factor it and get real factors. So they have to be real factors. And there's four possibilities that we're going to look at. One is what's called distinct linear factors. That means that's the normal kind of factoring we're looking at. You know, you have x squared plus something, and you get two factors, x plus or minus something and x plus or minus something. So they're two linear factors. Distinct means they're different numbers, because you can also get repeating factors. If you have a perfect square type quadratic in the denominator, you could get repeating roots. In this case, it's distinct roots or distinct factors. The second case is if you do have repeating linear factors. The third case is if you have a linear factor and a quadratic factor that you can't factor anymore. And sometimes you can actually have repeat quadratic factors. So two quadratic factors are the same, and they both have complex roots. So we're going to look at each one of these separately. The first two have similar techniques to solve. The second two use another technique. So here's just an example of what I'm talking about. So if we had the denominator being x squared minus 3x plus 2, we can factor that into x minus 2 and x minus 1. So those are distinct because they're different. But if I had the denominator being x squared minus 2x plus 1, then you have the same factor, x minus 1, or x minus 1 squared. So that's repeat linear factors. If you have distinct linear, and you can have more, you could actually have you could have a third order polynomial, and if you could factor that into the three linear factors, use the same procedure. So it's not limited to just two. It's not just limited to a second order equation. We're just going to mostly look at second order equations, but you could, as long as you could factor it, you can use this technique. Sometimes you factor a third order equation and one of the factors is real and the other one doesn't have any real roots. This, if you just tried to solve this, you get plus or minus the square root of -4, which would give you plus or minus 2i or something like that. So in this case, we can't factor it. So it has a distinct linear factor and a quadratic factor. Then you can also have the case where you would have two quadratic factors. That would have to be a fourth order polynomial to get that to happen. So the first two second order polynomials, the third one you at least need a third order polynomial, and the fourth case you have to have a fourth order polynomial. Like I said, you could have a distinct quadratic factor and two linear factors, and that you'd use the same techniques as this one here. It doesn't say single distinct linear factor, it just says I should say distinct linear factors, I guess. Okay, so you might have had this in pre-calculus. If you didn't, don't worry. We'll go over it in enough detail. So the first thing you do when you're looking at this, like for example, we could solve this problem now. We could use trig substitution. If I wanted to know what the integral of 1 over x squared minus 1 dx was, chapter 5 we couldn't do this because we could only do, the only integral that we could do back in chapter 5 would have been x times the square root of x squared minus 1 dx, which is very unique. This one doesn't have an x. If I let this be u, du would be 2x dx, but I don't have 2x in the, so I can't use any of the techniques that I learned in chapter 5, but I could use trig substitution. But it turns out I can also use partial fractions. So what I'm going to do is I'm going to factor the denominator. So you'll get x minus 1 and x plus 1. So you can see the inner and outer terms cancel out. But they are distinct because I have two separate answers. I have x minus 2 and x plus 1. So the whole idea here is to take that factored version and rewrite it as two separate fractions where the denominators of each separate fraction are the same as the factors of the original equation. They have to be that way. So when you have, what we're going to do is, so you say I need for this to happen, and then you combine these two into a single fraction. So the way you do that, when you have two fractions like this, you can just cross multiply this times that plus that times that. That'll be your numerator. And then the denominator is just the product of the two factors. All I'm doing there is multiplying this by x plus 1 divided by x plus 1. I'm multiplying this by x minus 1 divided by x minus 1 to get the same denominator. And so a gets multiplied by this, and b gets multiplied by that. And now if I compare the left-hand side with the right-hand side, you'll see they both now have the same denominator. So because of that, I can set the numerators equal to each other. And the question is, what values for a and b do I need to make this thing work out? So the way you do it when you do distinct linear factors is you're going to choose x equal to 1, and you're going to choose x equal to negative 1. So you let them equal to these values. And the reason you do that is if I let x equal 1, then the first term just becomes x, which is 1, plus 1. And the second term becomes b times x, which is 1, minus 1, which goes to 0. And so by choosing x being equal to 1, I eliminate me having to worry about calculating the constant b at this point. And so all I have is this term. So I have a times 2, and I divide, and I get a is equal to 1/2. And I do the same thing. I choose x equal to negative 1. What happens there is that this term goes to 0, and this other term goes to non-zero. So x is negative 1. This goes to 0. So I get b times negative 2, or b is equal to negative 1/2. So those are my constants. The other way, you could pick any two arbitrary values of x, and then you'd end with two equations and two unknowns in a and b, and you could solve them using substitution or elimination. But why make it hard? So we strategically choose x, the two x values, so that one of the constants is eliminated from the equation, so we can easily solve for the other constant. So what that says is that this original expression, 1 over x squared minus 1, is the same as 1 over 2 times x. Which one did they do first here? Minus 1. Minus 1 over 2 times x plus 1. So when I look at integrating it, I can say the integral of 1 over x squared minus 1 dx is the same as the integral of 1 over 2 times x minus 1 dx minus the integral of 1 over 2 times x plus 1 dx. And the answer here is 1/2 the constant times the natural log of the absolute value of x minus 1. And the second one is 1/2 times the natural log of the absolute value of x plus 1 plus c. Okay. So a lot of times you'll end up doing just these simple integrations, and you're like, what did you do there? Well, 1 over x, the integral of 1 over x dx is the natural log of x. And what I'm doing is that I'm letting u equal x minus 1, but dx is just du, so you don't get any kind of factors or any kind of sign differences. So it's just a simple, the integral of 1 over x plus anything is the natural log of x plus anything. So there's no point in making it longer than it needs to be. So I took an integral, which I did know how to do using trig substitution, but I can break it up into two integrals that are simple integrals, and I get the answer. So that's the whole concept behind partial fractions, and we will continue with that after the break. So that's it for today. I'm not going to assign any homework yet out of this chapter unless you like to work on it. And I will walk to my office and get a test if anybody wants to try to improve your grade. But if you have over a 90, you don't need to take the test. I'm not going to let you take the test.